moving on to some prerequisites for sensor fusion. What is necessary for us to be able to perform this sensor fusion? We're not going to cover everything because there are a lot of prerequisites, but we're going to go over just 2 or 3. So the first one we're going to be talking about is spatial synchronization. We're showing you here on the slide a vehicle with our frame of reference as we use it drawn on top of it. So our x-axis points to the right of the driver, y is going forward, and z is going up. We don't really use roll, pitch, and yaw at Civil Maps. We instead use omega, phi, and kappa as our angles of rotation. And omega is the angle around x, y, the angle around y is phi, and the angle around z is kappa. In the center of the slide, we're showing you the Atlas Dev Kit, and this is one of the products that we have here at Civil Maps, and we have different variants of this product with different sensors. In this particular case, we're showing you a Velodyne VLP16 model with an X-Sense and a camera there. And to the right of the slide, we're showing you the transformation between the LiDAR sensor and the IMU. So we're defining here the origin of our vehicle frame at the center of the IMU just for simplicity. And we're showing you the transformation, the actual number. So because the LiDAR is tilted forward by 30 degrees, you can see that the omega angle is negative 30 degrees. And similarly, x, y, and z are defined as a translation between the two origins. So how can we leverage this information? So let's say we are trying to figure out if a sign exists in the real world as we have it in the map. So the map is giving us some sort of hypothesis around where the signal is in the world. And as we're traveling through that environment, we're well localized, then we can take that map and put it in the field of view of the LiDAR. And what we will see then is the outline of the sign, our hypothesis, and we will analyze the points that fall within that outline to figure out if the signal still exists or not. So using these numbers on the right, we can project the map into the field of view of the LiDAR and get more information. Another prerequisite for sensor fusion is related to timing. So all the sensors on board the vehicle need to have the same concept of what now is. And luckily for us, we actually have a very strong signal, periodic signal coming onto the vehicle, and that's the GPS reception. So because we have GPS and usually the receiver is giving us data somewhere between 1 and 10 hertz, we can use this information to actually synchronize different sensors together. We're going to show you one example of how that happens, but before then, let's just think a little bit about how tight the synchronization needs to be. So we're going to take an example and do some back of the envelope calculation with you here. Let's say that we have two sensors, each one running at 1 megahertz. And we're synchronizing those two sensors with a 1 pulse per second signal going to both of them. So we have these two sensors getting a pulse per second telling them this is the start of the second. Each one of the sensors is running at 1 megahertz. They have, let's say, a 1 megahertz crystal with a 10 ppm error rate. So what that means is that each crystal can drift by 10 parts per million. So every million ticks of the oscillator, we can be off by 10. So let's say we have one sensor which is running a little hot, it's faster, the other sensor is a little slower than the real time, then our worst case drift is going to be by 20 seconds over a 1 second period. And then what would that mean in a real application? So let's say we have a vehicle traveling at 70 miles per hour, we're trying to synchronize the what each one of the sensors is observing in space. Our error would then translate to about 0.63 millimeters for those 20 microseconds of drift, which is still acceptable in an autonomous driving application. So even with a 10 ppm drift, our synchronization is still valid. And we can claim that it's valid because we know that the error, for example, on the LiDAR, which is one of the more precise sensors on the vehicle, is usually on the order of centimeters per point. So having an error of less than a millimeter in our position is not usually an issue. How do we do this synchronization? Well, we're talking about this pulse per second coming from the GPS receiver, and many receivers implement this signal, and they provide it with a nanosecond type of accuracy. So what we're going to look at is the Velodyne way of synchronizing the LiDAR to a GPS receiver. This is very similar to a Quanergy or different cameras as well that accept a pulse per second signal that allow them to be synchronized together. So we're looking at the top right of the slide at a LiDAR interface unit. This is a unit that usually comes with certain Velodyne models, and we've highlighted a couple of signals. So of course we have power and ground and all the Ethernet signals, but in particular here we're interested in the two signals that say GPS pulse and GPS receive. So as you might have guessed, the pulse is the signal which is responsible for getting that pulse per second, once a second, and then the GPS receive is responsible for getting a sentence over serial, essentially, that is telling it this is what time it is. So we pulse, we tell the LiDAR this is the start of the second, and then we follow it with a sentence saying here is what time it is actually right now. And that particular sentence is called the GPRMC sentence. Velodyne's LiDAR doesn't really care about the fields, let's say 3 and 5 and 7 and 8, and those fields define the position and the speed and the true course. But in particular, you have to get the timestamp, field number 1, and the date stamp correct so that you get a correct timestamp at the LiDAR site. Of course, the checksum is also important to make sure that the message is valid. So these were two prerequisites related to the hardware side of things, but what are some prerequisites for being able to use 3D maps as part of a sensor fusion system? It boils down to localization, and localization in 6 dimensions. So the reason we need localization is so that we can take the map and overlay it into a sensor's field of view, right? So let's assume the sensor is synchronized in space. We know its transformation to the vehicle origin. It's synchronized in time, so we know at a particular position what the information that that sensor is seeing. Then we really need to know where the vehicle is on the map to be able to overlay it into the sensor's field of view. What we're showing you here on the slide is some GPS traces from a fairly sophisticated IMU GNSS solution. So we took a Novatel, this is a $50,000 IMU, we put it on a car, we drove a bunch of times through downtown San Francisco and plotted the GPS traces. And this is a very good instrument with a fairly good antenna hooked onto it, but what you can see is the GPS is not reliable. And this is something that is well known at this point in the industry, especially in urban canyons. But even when we're driving with an open sky on the highway, right, the GPS can still have errors. In those two images, we're showing you in red a bounding box around where the GPS receiver and IMU GNSS solution thinks the vehicle is versus where the vehicle actually is, and that is done from our own localization and validated, if you at least want visually here, through the onboard camera. So as you can see, GPS can be in the next lane over, or it can be above the vehicle. So even if you're in the correct lane, if you're above the vehicle, you will not be able to project the map into the field of view of your sensors because your angles are going to be off. And that is necessary. So it's not only important to get X, Y, and Z correctly, but we also have to get omega, phi, and kappa as well.